Welcome. Uh, differential equation exam review. So we had the two lessons about differential equation. One just going over the basic terms and definition, and one looking at some applications. So the fundamentals of differential equation. So basically, we learn about the order of the differential equation, first order, second order. We learned about the linearity, linear or non-linear differential equation. We learned about like homogeneity of the differential equation, whether the differential equation is homogeneous or it has like source and sink term. And we learned about the type of differential equation, which is this is like an ordinary or partial differential equation. So which of the following equation represent a linear differential equation? This one, uh, no, it is not linear because it has like this transcendent. Oops, it has a transcendental function like cosine. So that's a transcendental function. So that's sine or cosine that would look something like this. That's not linear. Yeah. So this is like, is this linear? No, that's not linear. Yeah. How about this guy here? Is this linear? No, it's not linear. Why? Because I have y here multiplied by its derivative. So you see, like here, I have the y. It's multiplied like so. I have a function multiplied by its derivative. Like this term here is linear, so this is not linear. Yeah. How about this? Is this linear or no? No, this is not linear because I have like y squared. How about this guy here? This, yeah, so this is linear. This is like a constant. This is like linear second order. Again, this is a constant. This is like linear, and this is linear. So this is a linear one, and all these are not linear. Okay. What distinguish homogeneous differential equation from a non-homogeneous one? So remember, like a homogeneous one, that will not have any sources or sink term. Non-homogeneous one, homogeneous equation have no external forcing function. Yes. Homogeneous equation always includes a variable x. Means this is could include variable x, it could include variable y, it could include non-homogeneous equation do not involve derivative. Again, homogeneous equation contain a constant term. So basically, it has no external forcing function, like no source or sink term or any external forcing function. And please go to the lesson, check like the mathematical. This is just exercise, yeah, but just check the uh, check like the lesson and check the mathematical notations for like homogeneous and not homogeneous. Which of the following equation represent a non-homogeneous differential equation? So I can tell you this one. Yeah. Why? Because I have like the derivative with like respect to x, and I have here something which is like I have the derivative, so that's my function, yeah, dy with respect to dx, and then I have like y here, yeah, and I have like a 3x here. So that's like, for example, I am at the x, yeah, so you see here at like the x, see where I have like the x, like one of my independent variable, I have something that is function of x, so in my independent values. Which of the following represent a non-homogeneous differential equation? This one. Here, This one is homogeneous because I don't have, like, with respect to my like independent variable, I don't have anything here. How about this one? Again, this is homogeneous because with respect to my independent variable, I don't have anything here. How about this one? Again, this is homogeneous because with respect to my independent variable, like this guy, this guy, this guy, I don't have any forcing term here. Okay, so the correct answer is, like, you look at your uh, independent variable and you see you have any forcing term with respect to your independent variable. So that's basically like how you can know, like, whether this is homogeneous or not. We also look at, but again, check, uh, go back to this slides and check the details because there will be like some problem in the exam regarding this. Okay. While the conservation law are basis, like everything we do, like, all conservation law boil down to like some increase, decrease equal to a change. Like inflow minus outflow would be the change in storage. You can see like inflow over time, like inflow rate, outflow over time, outflow rate, change in storage, like time rate of volume may change. So you can have Q in, negative Q out, that would be the time flow rate of a change. That's basically like, so you see here, this rules, that's basically the everything we're doing, like boil down to this simple rule. And we have looked, for example, at the continuity equation is derived from the conservation of mass. So we looked at here, like you have a volume integral, you have a surface integral, and this volume integral and the surface integral is equal to the rate of a change of your mass, like m dot. That's the rate of a change. Like remember, like m dot, that is, that would be like, that would be, oh, that would be like dm over dt. That's like the dot, if you remember this dot notation here. So we have seen like for if there is like no sink or source term, like you don't have any rate of a change in mass, that would be like equal to zero if there is no accumulation, like basically like net flow equal is equal net outflow, like, so that's like in a steady state. So if you are in a steady state, like the inflow is equal to the outflow, then basically so like you do like your surface like integral is would be like equal to zero. So there's a compromise the cross section 1 and 2. So there's like you have no internal, like there's no change inside like your controlled volume, because what's coming in is equal to what's going out. So what's inside would remains the same. So you can have like this two surface integral, and then from this, like you can express, like you can integrate this over the area, and you can integrate this like over the area, and you can simplify like using this unit vector and this unit vector. You can go back to the original lesson and like see this details and explanation. But anyway, from this equation you can end up with like your simple continuity equation. Yeah, that's like like the velocity time acceleration here is equal to at any point inside your system, and is equal to at the exit of your system, and that would be equal Q. So basically Q as a constant. Yeah. So this would be important for your exam. Why I want this will be important for your exam? Like again, like this might, this is just explanation. You can look at it for your general like information, so you have some general knowledge. I mean, that's the general knowledge of the engineer basically. But what is more important than this general knowledge or general information would be, that's something very basic. which is, for example, like how to do unit conversion, for example, and how to ensure that your unit is consistent. So here I'm giving you Q in meter cube per minute and 12-inch diameter pipe. The velocity through the pipe is almost nearly, like I'm asking you for, this is meter per second. So you need to convert this to meter. So this meter, so you need to convert this to second, and you need to convert this to meter. And these are basic things like any engineer should be able to perform something like this. Yeah. So in the exam, basically, I will be very picky with respect to these types of things. Yeah. I would be very, very picky because I mean, you should not pass a course like this if you don't know this very basic thing, like how to, that your unit should be consistent and how to convert between units. Okay, so that's something that you need to pay attention to. Okay, this is just like another example, like so you can look at this example, but the main focus of this example would be like on unit conversion and unit consistency and things like that. That would be the main focus of this type of problem. We also like learned in this lesson how to just use laws of conservation to formulate a differential equation. So analytical solution of first all the linear homogeneous differential equation solved by the separation of variable. So like you read the problem and then you formulate your differential equation. So change of like m over t, that's like m dot, yeah. That's the rate of salt entering and the rate of salt leaving. So you can read this problem, formulate it until like you get something that looks like this, yeah. And now when I get something that looks like this, I know that how could I do this? I could solve this by separation of variables. So I have two variables. I have like dm here, and I have like, so that's two variables. I have dm here and I have dt here. And that becomes simple because now I integrate with respect to dm here, and then I integrate with respect to dt here. So the left hand side, I integrate this with respect to dm. The right hand side, I integrate this with respect to dt. So that would be like something like len something. That would be like dt, that would be like d, and then like you can use some algebra to get like the terms together, and then you will have some initial condition which you can use to find the constant, because here you have a constant, so you can use this initial condition to find this constant. And then there's a differential equation for the amount of salt in the tank. So now you have an equation that tells you mass as a function of time. Yeah. So, and then you can just use this equation. You have an analytical solution. So this is my differential equation. It looks something like this. The analytical solution of this differential equation is something like this. And then if I know this analytical solution, I can just find the mass in the tank at any given time. So at 10 minutes, for example, I substitute like 10 minutes here, and then that's like 9.52 kilogram. And then I could, the limiting amount of salt at like, as time approaches infinity, so basically that approaches infinity, that would be zero, that would be like 100 kilograms. So that would be the limiting amount of salt. Okay, so that's basically like the differential equation. You see how to go from the laws of conservation, you use them to form your differential equation. You use your knowledge of calculus, integral calculus in that respect to like solve differential. So we solve differential equation by integration. So we do integration here, and then we have we use our initial condition to find the constant, and then we will end up with this analytical solution. So here, this is the analytical solution for my differential equation. So that's the differential equation. That is the analytical solution. And then you can use this analytical solution to learn about your system. So here you can pause like the video and go like through this table just to see the difference, like the concepts that we covered. Again, this would be general knowledge for any engineer. Yeah, uh, because that's what engineers should be good in math. Like I remember, I used to work before in agriculture research center in Ireland or wherever that is, and whenever they have like a math problem, something that's related to math, they will come to me because this guy's the engineer. He should be good in math, yeah, and he should understand like this all these mathematical concepts, and I used to help them and solve them. Yeah. Okay. So that's I think all for. We still have. That's just the basic concepts. Then we looked at also the application of this differential equation. So here, for example, like this is something that you should be able to understand. Like so, when you look at this, you should say, okay, this is a partial differential equation. It is non-homogeneous. Why it's non-homogeneous? Because sorry, it is non-linear. Why it is non-linear? Because I have here h is multiplied by its my dependent variable is multiplied by its derivative. And it is not in a transient state because it is delta H is changing with time, so it is not in a transient state. So I have it's not like sorry, it's not in a steady state. Yeah. But here, like when you look here, you have like this parameter. So this one of your model parameter, and this model parameter here, it's a function like so. K will change in the x direction here, and k will change in the y direction here. Now, if k is constant in the x direction, so here, for example, let's say like k in the x direction would be like larger than k in the y direction. Here, for example, when I remove this x here, this means that like this parameter in the x direction, it has the same value as like in the y direction. So and so this like it's the same, like it's the same value. Yeah. So but here this parameter, that's very important. It is a function of x, so which means that like let's say this is my volume here. Let's say this is my x here. So like k here would be like difference, and like k here would be difference, and k here would be, yeah, is it changing in x. Yeah, and that's why I have this k inside the this inside like here inside the side like this derivative. Yeah, so I have the k inside. But if k is constant, like k across all x, like this parameter across all x is the same, yeah, then I can just get it out of this derivative. Yeah. If my function is steady state, it's not changing in time, this means that this is zero. Then I got like this form of equation. So this form of equation will assume that, and here in that case, I can take k as a common factor. Yeah, and just like get rid of it. Because if you take k as a common factor, you divide by zero, that's like zero. And then like I got this form of equation. So this would be like a nonlinear second order partial differential equation. Second order, yeah, because I have it's like the delta x and delta x, so that's the difference of the difference. Yeah, that's why it's like a second order. Yeah, and nonlinear because my independent variable is multiplied by its derivative. Steady state because it is not changing in time, and partial differential equation because I have two independent variable like delta y and delta x. Yeah. So that is something you can. Oh, I don't want to change this. We also looked at the system of ordinary, for example, differential equation. I mean, sorry, it's like smeared on the screen here, but you know what this is, yeah? That's like, let me write it down here. dx over dt, yeah, is equal to x a negative by, yeah. Uh, so we looked at like a system of differential equations that would depend on one another. So here like dx over dy, dy over dt, and here's a function of x and y, and here's a function of x and y. And this is called like the predator prey model, and you can like check these details, but this model does not have like an analytical solution except for like the trivial case where it's like in a steady state, like dx and dt and dy dt is equal to 0. So that's like would be the like when this is equal to 0 and this is equal to 0, then you can just solve for x and y. But that's the trivial case. But for the non-trivial case, has no analytical solution, and then you have to solve this numerically. And we have seen like how these models could be just not necessarily studying a population of predator, that's like a fox, and a prey that's rapid, like if you are only studying ecology, but it could be useful to study different types of relationship. And I showed you, for example, how to actually you have already did some Google search and found like how to use this in your own applications, yeah, that of your interest. So we talked about this is like the trivial this is a non-trivial like solution when at steady state, for example, like you can do this. We also looked at another type of this system of ordinary differential equation, which is the Lorenz equation for chaotic system, and that was mainly for it was used to for weather prediction, weather forecast, yeah. And so you have like this equation. It's basically like you're looking at three variable. Like in the previous one, you were looking at two variables, the population of foxes and the population of rapids. But here you are looking at three variable. You're looking at the rate of atmospheric fluid motion and the horizontal temperature and the vertical temperature. So basically, like you were looking at the motion x as a function of like how wind would move as a function of vertical and horizontal temperature with some constant and some geometric factors, yeah. And we have also seen that this the most important thing about this Lorenz equation for chaotic system is that you see that like these systems are very sensitive to the initial conditions. So if I just made like tiny little change to my initial condition, yeah, just tiny little change, it will affect the solution. It will affect the solution yeah, uh, uh, it will affect the solution like at like later in time, yeah, where you get like very different solutions. That's why we cannot like do weather forecast beyond like a certain numbers of day. Like we cannot do long-term weather forecast. One reason why we cannot while long-term weather forecast is because of this like Lorenz equation, and you can check back the video, yeah. So the predator prey model, so that's like has an analytical solution for the case of equilibrium. Yeah, this is true. Numerical solution for the case of non-equilibrium. This is true. Analytical solution for cases of equilibrium. This is wrong. So basically, that would be the correct answer. So here, that's the correct answer. Okay, so you just like need to understand like this basic concept. Okay, so that's all for this lesson, and yeah, see you in the next lesson.